Structured text files are a common data storage method, such as this score.txt file, which records the scores of students in all classes. The first row is the column name, and each subsequent row is the data of a student, separated by tab within each row. This structured text also has various computational and processing requirements. For example, selecting the girls with the English score of 90 or above. Calculate the total score of each student, and sort them in descending order. Calculate the average Chinese language score for each class. Importing into a database and using SQL to calculate is certainly not a problem, but the process is complicated and there may not always be a database available. Writing Java code is also very tedious, but using SPL is very simple. First, let's see how to load the file. The import function of A1 can directly read the structured text file into an in-memory data table. The @t option represents the first row as field name. For comma-separated CSV files, the option @c can be used to read in, and @tc represents reading the CSV text with the first row being column names. Read score.txt and score.csv respectively in A1 and A2. A3 and A4 can also read score.txt and score.csv using the t function, which can automatically load based on the file extension name. There are other situations when reading text data, such as not having a title row, only reading partial columns, custom separators, and text with quotation marks and carriage returns. For details on these functions, please refer to the official documentation. Let's first try the filtering operation, for example, to select girls who score 90 or above in English. A1 uses the t function to load text data into an in-memory data table, using the select function to filter the data in A2. It can be seen that only girls with scores equal to or above 90 remain in the result. The dot operator in A3 can combine loading data and filtering operation into one statement with the same calculation result. Sometimes it is desired to dynamically pass in the values of the filtering criteria. The default values can be predefined as 80 points in male students, which can be modified during runtime. The select function in A4 can use these two parameter variables. The result after running matches the parameter values. In A5, use the export function to write the result table sequence of A2 back into a text file named filter.txt. Similar to the import function, the @t option indicates that the first row will be written as a title. If this file is regarded as a table, the corresponding SQL statement for the operation is as follows. Then try some aggregation operations. Calculate the highest and average scores for both girls and boys separately, which is consistent with the SQL aggregation functions. After the initial calculation attempts, let's take a look at how to integrate these codes into Java applications. SPL offers standard JDBC, which can provide data querying and computing capabilities to Java applications like executing SQL or calling stored procedures. Just need to import these two jar packages into the application. Then place the SPL configuration file in the application class path. Racksoft config XML is the core configuration file of SPL, and its name cannot be changed. Let's first look at the situation of directly executing SPL statements. The driver class is internal driver. The connection URL is JDBC, SPROC, local. The created JDBC connection can execute SPL code like in SQL query. Load score.txt here to filter students with high scoring English. Use JDBC parameters to dynamically set the minimum score, with 90 set here. Run this Java program and, like other regular JDBC uses, return the result table sequence as a result set object. Then look at the way to call an SPL script. Save the SPL program as a SPLX script file, here saved as scorecalc.splx. Put the script file into the main directory of SPROC. Then you can call these scripts like using JDBC to call stored procedures. Executing call scorecalc calls and execute scorecalc.splx. Return the result set to result set. In addition to returning a table sequence of multiple rows and columns to the JDBC result set object, it can also return a single value of one row and one column, or a sequence of multiple values of multiple rows and one column. A single value with one row and one column, with the column name fixed as field. For example, A2 returns the total math score of 70,360. Multiple values with multi-rows and one column, with the column name still being field, such as A5, returning the total score, number of people, average score, and lowest score in mathematics. Next, let's continue to look at more computing tasks, and implement common SQL operations using SPL. For the convenience of discussion, we assume that all A1 cells of the code are to load the file, and then assign the table sequence to the score variable. Afterwards, there is no need to write A1 anymore, only calculate on score. In addition, for simplicity, SPL code no longer uses parameters, and you can modify it to have parameters by yourself. Calculate a new field using multiple field values of the same row. For example, calculate the total score and average score of each student's 3 subjects. SPL uses the new function to define calculated columns, and the expression in the calculated column can use the existing calculated columns, such as calculating total first and then using total to calculate average. In the new function, some original columns can also be selected and mixed with new computed columns, or adjust the order of the columns. Here, the gender is adjusted before the name. If you want to add new calculated columns directly to the existing table sequence, you can use the derive function. Add the total and average scores of the 3 subjects here. Sort all students in descending order of total score, and for students with equal total scores, sort them in ascending order of math scores. SPL uses the sort function to implement sorting, with a negative sign before the sorting field, total, indicating descending order and math, indicating ascending order. In the results, it is observed that there are multiple students, with a total score of 281, with students with lower math scores ranking higher. Fields of string and date types also support sorting. For example, to sort in reverse order by name will compare the characters one by one from the first character to the next. We want to group by class and gender, and calculate the number of people and average English scores. SPL uses the groups function to implement grouping and aggregation. Define the grouping field's class and gender before the semicolon in parameter. When there are multiple grouping fields, separate them with commas. Define the aggregation expression after the semicolon, supporting aggregations such as sum, count, average, min, max, etc. Before grouping, use the select function to filter students who score 60 or above in mathematics. After grouping and aggregation, use the select function to filter groups with an average English score exceeding 70. SPL is defined and calculated step by step, and intermediate steps can be filtered at any time without using where and having to distinguish whether it occurred after the grouping. In SPL, using the ID function can remove duplicate values. After removing duplicate names for 1,000 students, we see 598 names. Multiple columns can also be combined to remove duplicates, which means that the values of multiple columns are considered duplicate only when they are all the same. For example, if 1,000 students combine name and math to remove duplicates, there will be 992 left. In SPL, the iCount function is used to implement count distinct, resulting in 598 names after deduplication among 1,000 students. iCount also supports multi-column count distinct, with 992 remaining after deduplication for names and math scores that are all the same. The iCount function can also be used within the groups function, allowing for count distinct within the groups. There are 54 names for 56 people in class 2 and 53 names for 55 people in class 3. It is also common to calculate the top few records, and the top function gets the top in records. The first parameter is a negative number, indicating reverse order. -5 will get the top 5 records with the highest total. If it is a positive number of 5, it will get the bottom 5 records with the lowest total. When getting the top n, duplicate values will occupy the ranking by default, such as the 4th and 5th both scoring 281. If you want duplicate values not to occupy the ranking, you can use the edit option. Among the top 5, if the 4th has duplicate values, and there are a total of 3 people, then a total of 7 people will be found in the top 5. To find the maximum and minimum records, can also use the maxp and mint functions, which are equivalent to top1 and top-1, respectively. To find out the top 5 students in each class, you can use the top function and the group function. The top 5 students from each class as shown in the figure are a series of subsets. Clicking on class 3 will reveal the top 5 students from class 3. The groups and group functions are both used for grouping. Simply put, the former calculates some aggregation values directly after grouping, while the latter obtains subsets of each group after grouping. The subsets can be flexibly defined for more calculations, and may not always be aggregated. SPL provides many related calculation functions for different types of data. Here listed some calculations based on the send and receive date fields, to obtain the year, month, day, and day of the week, to calculate how many days and weeks there is a difference between 2 dates, and to calculate the new date after a date. There are also many calculation functions for string-type data. Multiple strings can be concatenated together using concat to determine if all characters are lowercase letters, to convert to lowercase, to truncate left, right, or middle substrings, to match strings with wildcard characters, to replace strings, and to randomly generate new strings of specific lengths using certain characters. SPL provides conversion functions between date and time, various numerical values, and string types. The target type is used as the function name, and the function automatically determines the original data type, and correctly converts it to the target type. For example, the date function can pass in integers such as year, month, day, string date, and can also specify the parsing format of the string date, ultimately obtaining a date. There are many numerical types, including integer int, long integer, double precision floating point number float, real number, and large floating point number decimal. In addition to converting between various numerical types, string and date types can also be converted to numerical values. When converting date, time, and numerical values into strings, the format can also be specified. There are more calculation functions available, which can be viewed in detail in the official online documentation. Next, let's take a look at operations involving multiple file associations. SPL regards associations differently from SQL, as it distinguishes between foreign key associations and primary key associations. For example, if the city foreign key in the student table is linked to the primary key city ID in the city table, this is a foreign key association. The ordinary fields class and school in the student table are respectively linked to the primary key's class ID and school ID in the class table. This two-field and multi-field association is also a foreign key association. The student table is associated with the primary key student ID of the student health table using the primary key, which is called primary key association. These two tables have a one-to-one relationship, also known as a homo-dimensional table. The student table is associated with the student payment table's partial primary key student ID using the primary key, which also belongs to primary key association. These two tables have a one-to-many relationship, also known as the primary subtables. Based on different association characteristics, SPL uses different functions to distinguish and implement associations. Association operations involve multiple files. Similarly, in A1, multiple texts will be loaded as SPL table sequence variables to facilitate subsequent calculations. There are class teacher ID, English teacher ID, and other information in class.txt, while teacher.txt records the teacher's name, gender, and subject being taught. We need to find out the classes where the class teacher is a Chinese teacher. It is necessary to associate the class teacher in class.txt with the teacher ID in teacher.txt. SPL uses the switch method to join two tables. During the calculation process of A2, 4 table sequences are involved, with class.txt loaded as the table sequence class and teacher.txt loaded as the table sequence teacher. Then use the switch function to replace class teacher field value of the class with the relevant record of the teacher, and calculate the CT table sequence. The field values of the SPL table sequence, can be complex data types such as records or even sub-table sequences. CT is a multi-level nested table sequence. It is not difficult to obtain data from nested sub-records. For example, when CT2 with a simple structure is generated by CT_new, classTeacher.subject obtains the subject taught by the class teacher, and finally uses the select function to find the Chinese subject. The from city field of the student table is foreign key to the city table, the class ID field is foreign key to the class table, and the English, Chinese, and mathematics teacher fields in the class table are all foreign key to the teacher table. The student table has 2 foreign key fields, and the class table has 3. There is also a multi-level association between the student table and the class table, and between the class table and the teacher table. To query students from City 4 and whose teacher is Teacher 8, 4 tables need to be associated together. The switch function supports associating multiple foreign key tables simultaneously. In A2, first associate the class table with the 3 subject teachers, and then associate the city table and A2 the class table in B2. The result of B2 association is a more complex multi-level table sequence, which can visually display the association results. Finally, in C2, use the new function to extract the required information from the table sequence at each level, and filter out students from City 4, who are taught by Teacher 8. The switch function is suitable for single-field foreign key associations, and when multiple fields are associated, the join function should be used. Add a school column to the score table to record the scores of 30 classes in 5 schools, with 6 classes in each school. The class table records these 30 classes, with the primary keys being the class and school fields. The classes are classified into Type 1, Type 2, and Type 3. Now we need to find out the scores of all students in Type 3 classes. In the parameters of the join function, before the first comma are multiple foreign key fields, class and school. Before the second comma is the associated table class, along with its multiple primary key fields class and school. After that are the target fields selected from the associated table, which can be multiple, and we only selected one class type field here. The switch function is for single field association that supports multiple tables, resulting in nested multi-level table sequences. The join function can support multi-field association, but not multi-table. The result is to directly join the fields of 2 tables to form a single layer structured table sequence. The primary keys of the student table, family table, and health table are all student IDs, and the 3 tables have a 1-to-1 homodimensional relationship. The latter 2 tables provide supplementary information on different aspects of students. The primary key association requires the use of a new association function, such as join A, B, C, which defines information for multiple associated tables in the parameters, the associated table, student, the field name, stu, in the table sequence after association, and the associated primary key, student ID. Observing the association result of A2, the 3 table records with student ID 2 are associated together. After association in A2, A3 filters out students and parents with myopia degree exceeding 500 degrees. Another type of primary key association is the primary subtable, where the student payment table, pay, is a subtable. It has 2 primary keys, student ID and pay date, and uses the student ID as a foreign key to the primary table student's primary key. The primary subtable also used the join function to associate. A student has 5 payment records, and each payment record is associated with the student record in the primary table. After association in A2, A3 uses the groups function to calculate the total payment amount for each student. The above is the content of structured text calculation in SPL, which provides a simple and powerful calculation solution for data outside of databases. The examples involved here are all small data that can be read into memory. For files larger than memory, SPL also provides a cursor solution for calculation. Interested friends can refer to SPL's official documentation. Of course, SPL's capabilities go far beyond that. SPL also supports various text formats such as JSON and XML, cross-database queries, and supports mixed computing between databases and other non-databases, supports for big data or complex computing, and SPL's computing power, can also be used to optimize SQL performance. We will gradually introduce these contents in later topics. SPL is an open source software that can be obtained from GitHub.